Hey, hi there. Welcome to today's video. In the previous videos, we have finished till probability introduction. And today we'll be starting off with the first session or first chapter of probability distributions. So basically we'll try to see how the distributions are created with respect to both discrete and continuous variables. So let's get started. So whenever we try to understand probability distributions, we always talk about random variables. So all these data points, which we will get through Excel sheets or we pull it from a server, we consider them to be random variables. Now, variables itself can take multiple values, right? But what makes a variable random is the frequency attached to it. It's a frequency associated with it. The fact that we, create an interval for continuous distributions and then plot the probabilities in the form of a histogram, it makes that particular X or it makes that particular event as random variable. Suppose salary can be a continuous set of values, right? And when you plot in a histogram, right, it will look something like this, like a bell curve. And that is a property of a random variable. So my salary is basically my random variable. On the either way, if you talk about discrete data points, like let's say ratings between 1 to 5, and if I do a simple dot value underscore counts dot plot kind is equal to bar, I can express those ratings as a form of a bar plot or a count plot, right? So let's say it's discrete, so it will be spaced. So this is 1, 2, 3, 4 rating, right? This is also a probability distribution because we're plotting the frequencies. We can convert this to a probability easily because once we have frequency, we can convert it to a probability. Frequency divided by total number of observations or data points is nothing but my probability. So once we have the probability, this becomes a probability distribution graph because you're plotting the probabilities along with the events, which is X, which is nothing but the data points. So these X rating is also a random variable. Okay, so random variables can be, out of two types, right? This random variable are of two types. One is discrete random variables. Under discrete random variables, which is for discontinuous variables, right? And we have Bernoulli distribution, we have binomial, Poisson, geometric distributions. There are other distributions as well, which fall under the category of discrete random variables. So discrete data points can be modeled or can be said to follow one of these distributions. On the other hand, we have continuous random variables as well. And the corresponding distributions are normal, which is pretty much very common, right? Normal, we have a Gaussian distribution, we have student distribution, we have log normal, exponential, variable, Gumbel, gamma, whatever it is, right? There are other distributions as well, which are continuous, right? So random variables can be broadly classified into two types, discrete and continuous. So you can understand that the first chapter of statistics, what we're trying to understand, what are different types of data which we come across, right? One was one was qualitative, one was quantitative. That is all what I'm talking about here. This is kind of, it went treated as discrete as well as categorical. This is continuous. Although we see here the random variable typically is a number, but yes, even if we have ratings or even if you talk about, say, number of cities, right? Cities column can also be treated as a random variable because we have different cities and we can find the count of all these cities in the data set, each and every city in the data set. Okay, so what is a random variable? Random variable is nothing but it can take a finite number of values, okay, and it has its own associated frequency or probability. So I've noted down some definitions here for your benefit, but ultimately the game is all about first identifying whether the column is discrete or continuous. If it is discrete, we'll use a different set of visualizations, different set of pre-processing, different set of probability distribution techniques. If it is continuous, it will be different. As I give an example, if I ask you what are the what are the natural numbers between 1 and say 100, we can easily discretize it. You can call it 1, 2, 3, 4, 5. But if I ask you what are the set of all possible numbers between 1 and 100, it can be anything 1.001. So that becomes continuous. The conceptual understanding of continuous and discontinuous typically come when you practice data sets, guys. So after this video, we'll get our hands dirty with Python, right? We'll do some case studies or we'll do handle some data sets. So that is where it's very important that you go to the application part also along with the theory which I'm teaching in the slides. Okay, so let us take some examples, and today's topic will be primarily consist of discrete random variables. In the next session or next chapter, we'll cover continuous distributions. So let us take some example of discrete random variables or discrete distributions. So you can see here coin toss, die roll, making 100 sales calls, 150 questions. Like these are discrete data points. Count the number of vehicles passing through a toll booth. Maybe discrete, maybe continuous also, but yeah, typically we can consider it as discrete. So it depends on the data set which I'm getting. If the data set has too many unique values, then that tends to be continuous. It has less unique values, then those data points are discrete. Okay, so just to give an example of a few of the discrete random variables. Now, what is the probability distribution? How does the probability distribution of a discrete random variable look like? The probability distribution of a discrete random variable is nothing but the relationship between each possible outcome or event, what you can call it, of a random variable and their associated probabilities. Okay, it can be a graph, it can be a table, it can be a formula. How it can be a graph? Graph is very simple, where you have on the x-axis we have the events, possible outcomes, and the y-axis we have the probabilities. It can be a table. Table-wise, we have the values of x and the corresponding values of p in 2 columns, right? It can also be a function. So basically, probability is a function of the x. Now, this function, based on this type of function, we have different types of distributions, different types of probability distribution. Just like we saw, we have geometric, we had binomial, Bernoulli, Poisson, all these things, right? So let's have a look. So you can see here, right? So this is my x, team 1, team 2. Now, so see, team 1 is string, right? But it can be taken as a random variable. Okay, not a problem. But it is discrete, obviously, right? Team 1, what is the count of T1? What is the count of team 10? So these are all frequencies, but we can convert it to a probability, right? We can add all these numbers to get the total n and divide it by. So 24 divided by all the counts will give me the probability of team 1. Very simple. That is what we can easily do. Okay, same thing. So this is how it is represented by a count plot, and it should have spaces between them because this is discrete data points. It's not continuous like a histogram. Histogram is continuous, and the height represents basically the frequency or the probability. In this case, it's frequency. We can convert to a probability. Okay, great. Necessary conditions for a random discrete variable. So what are the conditions? Yes, the probabilities have to lie between 0 and 1. Obviously, the probability has to lie between 0 and 1, and the summation of all the probabilities will be equal to 1. Of course. Now, if I, let's say, add all these probabilities, it will be 1. Okay, so 24 divided by all these observations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values we have. So 24 plus 36 plus whatever it is. This will give me some probability. This will give me some probability. And if you add all these probabilities, obviously it will be 1. Right? Correct? Because we're adding the probabilities of all possible outcomes of the experiment. We have already discussed this in the introduction to probability video. Okay. So now let us take some examples to understand it more clearly. Let's say we take an example of a coin toss. Okay. Just focus on the point where I'm placing my cursor, guys. Okay. Suppose say this is the first question. What is the question? A coin is tossed. Count number of heads. Okay, or plot the distribution table, whatever it is. So if a coin is tossed, we have 2 possible outcomes. Of course, one is 0.5. One is tail, whose probability will be 0.5. The other one is head, whose again probability has to be 0.5. Again, sum of total probabilities will be 1, right? Okay, so now how do I plot the distribution graph? Very simple. I'll have to plot all possible outcomes on the x-axis and the corresponding probabilities on the y-axis. Okay, so I can model them as 0 and 1. That's what I'm trying to say here, guys. Don't get confused, right? I can replace tail with 0 and head at 1, or I can do the reverse. Doesn't matter. We can basically we can try to use a number to indicate heads or tails. And if you're talking about count number of heads, so since they are talking about number of heads, so if it is tail, then my number of heads will be 0. If it is head, my number of heads will be 1, because only there is 1 coin toss. You can think of it like that also. So ideally, we can use it as 0 heads and 1 heads. 0 heads and 1 heads. 0 heads means tail, 1 heads means 1 head. That's it. Okay, that's why I'm writing it as tail directly here. So now if I change the question to 2 coin tosses, how does it change? Because now we have 2 coin tosses. In 2 coin tosses, we can have tail tail, we can have tail head, we can have head tail, we can have head and head. So if I talk about count the number of heads in each of these events or outcomes, we'll have 0 because it's tail tail, 0 heads. Here we'll have 1 head, here we have 1 head, and here we have 2 heads. So ideally, if you look at it, total number of events or possible outcomes which we have is 3 only, because we can either have 0 heads, or we can have 1 heads, or we can have 2 heads, not more than that. So actually there are 3 cases here. This should be actually 3 cases, right? Because these 2 can be modeled as a single case. That's why I'm directly plotting the cumulative probability of these 2 cases directly here, right? So I have 0 head event, 1 head event, and 2 heads event, of whom 1 head event has a 50% probability raised to our 0.25, 0.5. Total probability again has to be 1. So this is actually, we can model it as 3 cases. X comma px, nothing but the coordinates, right? For 0, it is 0.25. For 1, it is 0.5. For 2, it is 0.5. Here, guys. So let us take an example. Let me plot the probability distribution of my workout schedule. Okay. So, and I'll take the number of workouts which I do in a week as X. Number of workouts means how many number of days do I go to the gym in a particular week. So let's say this is my probability distribution. Say I do not go to the gym in a week at all, and that probability is 0.09. If I go to the gym 1 day in a week, its probability is 0.15. I have a 40% chance of me, there's a 40% chance of me going to the gym 2 days in a week, right? And that is how we have, suppose they have calculated the probabilities based on my past behavior, right? Now, if I want to calculate the mean and a standard deviation, how do I do it? Very simple. I'll calculate the mean using this formula. Very simple. Summation of x into p of x. How? Very simple. So if I suppose, let's say, how did you find the mean before? With frequency, summation of fi xi by n. This is what we did. So if I divide the individual frequencies by the total number of occurrences, what will we get? Let's say, so this is nothing but f1 x1 by n plus f2 x2 by n plus dot f3 x3 by n plus dot dot dot. Now this f2 by n, f3 by n, f1 by n can be written as p1 into x1 plus p2 into x2 plus p3 into x3, because f1 by n is nothing but my probability. Frequency divided by total number of observations gives you probability. And this means that this is nothing but summation of pi into xi. So this is what it is. Clear? Similarly, I can find out the variance, right? Summation of x minus mu whole square, which is your sum of squares into p of corresponding p of x, right? And this is called as variance. So if I want to find out the standard deviation, I have to take the square root of the variation or the variance, which is nothing but 1.38. Square root of 1.93 is basically your 1.38. Okay. So now, if I want to visualize this workout schedule routine, right? I'll take the table first. Okay. So here we can see all the necessary required table which we already have, and then I'll draw the corresponding graph. Right. So here you can see that 0 ke liye it is 0.09, for 5 it is 0.01, and I have the maximum probability of me going to the gym when I go to the gym for 2 days. So me going to the gym 2 days has the maximum probability. And hence you can see the mean which we had calculated before, it was 2.15, which almost lies around this maximum probability, the event which has the maximum probability. Makes sense? Okay, so this is an example of discrete distribution. Okay. So basically this is a bar diagram. This is what is called as a bar diagram. Okay. Now let us try to deep dive into some distributions which have some typical characteristics. Although they are all discrete distributions, but they have some discrete, they have some unique features associated with them. Some distribution can be typically used to model a particular kind of behavior. Right. So let's see what are these behaviors and what kind of distributions are available for us to model them. Okay. What is Bernoulli distribution? The first distribution is Bernoulli in discrete distributions. So basically, it's a model for an experiment that has only 2 possible outcomes, either 0 or 1. So basically, it has got 2 outcomes, 0 or 1, yes and no, true and false, on and off. All these kind of outcomes can be modeled using Bernoulli distribution. So outcome do ही है, right? A and B, correct? And so the corresponding probability mass function, sometimes we call it as probability mass function, sometimes we call it as probability density function. For discrete distribution, typically it is called as probability mass function. For continuous distribution, it will be called as probability density function. Probability mass function or probability density function is nothing but the expression which gives you the probability calculation. P is equal to f of x. This is your probability mass function actually. Okay, so let's see what's the formula. This is your formula. What does the formula say? It has got 2 probabilities, right? Correct. For x equal to 1 or x equal to event A, P. For x equal to event B, it will be 1 minus P. So true के लिए अगर P है, false के लिए 1 minus P होगा. On के लिए if it is 1 minus P, off के लिए P होगा. So of course, since there are 2 outcomes, if one probability is 0.7, the other probability has to be 0.3 because total probability has to be 1. Let's say give an example. Suppose the probability of 1, right, is 0.6, which is this. The probability of 0 will be 0.4, right? So now how do we calculate the average or the mean value and the variance, right? So the average value is given as P. So the probability of that particular event under question is given by P, and that is what it is. And the variance is given by P into 1 minus P. Very simple. And if I want to take the standard deviation out of it, they have to do root over P into 1 minus P. Okay. So next, which we have is called as a binomial distribution. So what is a binomial distribution? It is the number of successes X in repeated trials of a Bernoulli experiment. So basically, it's the summation of multiple Bernoulli trials, right? Previously, say a coin toss. A single coin toss is an example of Bernoulli. Correct. Number of hits, if I consider the probability of hits as P, which is 0.5, the number of probability of tails will be is equal to 0.5 again, right? P. So if I have, so let's again take the example of the coin toss. Let's go back to the coin toss. So this was the coin toss example, right? A single coin toss is an example of Bernoulli. Why? Because it has only 2 outcomes. One thing's for sure, both the probabilities are same. But if I have the probability of hit, the other one is nothing but 1 minus 0.5. Right? Correct? Same way. The average value will be 0.5. Standard deviation is 0.5 into 0.5. That is your Bernoulli. But if I repeat the same coin toss, or this one coin toss is called an experiment or a trial, right? If I repeat it, multiple times, that becomes a binomial distribution. So this is actually a binomial distribution because we have multiple trials or multiple experiments here, 2 coin tosses. Correct? Okay. So a binomial distribution is nothing but the number of successes. The number of successes X. In this case, number of success where success is considered as me getting ahead, right? So binomial is nothing but the number of successes repeated in multiple trials of the Bernoulli process. In multiple Bernoulli processes. So each of these events is actually a Bernoulli process. But the problem is, since we are doing multiple number of times, the number of total outcomes of that particular event, which is head, will no longer be 2, it will be multiple, obviously. Correct? Okay. But if I talk about the individual, if I talk about the individual trial, it will only have 2 outcomes. Clear? So this is a Bernoulli and this is a binomial. So let's get back to the slide. So what is the PMF? Again, the probability mass function. It will be again a function of the X, right? P is equal to F of X. Let's see. So this is your probability calculation function. Now I understand it looks a little bit scary. This is nothing but NCX, right? Combination X, P to the power X, Q to the power of N minus X. Q is nothing but 1 minus P. I can write this as 1 minus P. Okay. Now, if you look at it, it's pretty much difficult to remember. And we don't need to, guys. We have a straightforward function in Python from scipy module. There we have a function which is called as stats, and inside it we have a function which is called as binom. In the binom function, these parameters we have to put in. So what are the parameters here? If you look at the parameters, we have number of trials, which is n. P is the probability of the success. Okay, the probability of the question which is we are asking. Heads chahiye ki tails? We're asking for head or tail. So that is your P value. And the corresponding other probability will be 1 minus P or Q. Okay. X is nothing but the event, like X, how many number of events we're asking? 0 heads, 1 head, 2 heads, 3 heads, that is X. That we can calculate. So based on the value of X, we get different probabilities in this particular function. Okay. Let's see. Right? Q is nothing but 1 minus P, and equal number of trials, number of successes, probability of getting a success in one trial, probability of getting a failure in one. Very simple. Okay. This is 1 minus P. And typically this is how my graph looks like. If I keep on plotting different values of X, let's say I pick up probability of P is equal to 0.5 and N is equal to number of trials, 20, right? Probability in this case is lesser, 0.5. Blue may 0.5, this is for probability 0.5, and this is for probability 0.7 of a success in one trial. Right? And this is again 0.5, but the number of data points, number of trials, sorry, is more. So if you look at the number, so in this case, the number of trials is same. Now, if you look at it carefully, right, the probability is high of one success in one trial. The graphs tend to shift towards the right, correct? Okay. Because this is for 0.5 and this is for 0.7 with same number of trials. But if you keep on again increase the number of trials from 20 to 40, the distribution becomes a little bit more symmetrical, or I can say a little bit more uniform, less skewed. Becomes less skewed. The distribution becomes less skewed, as if it is trying to approach or mimic a bell curve. But my bell curve and normal distribution is continuous. This is discrete. So when you increase the number of trials, a binomial distribution may tend towards a normal distribution because you have increased the number of trials so much. This is called as normal approximation. Normal approximation. Okay, we'll talk about it later on. We can study about it. And that is why in corporate, when we have sufficient amount of data, huge amount of data. We typically don't tend to bother to find out what distribution it follows. If it is discrete, we simply do the bar plot, we do some calculations based on that. And if it is continuous, we treat it as a normal distribution. We don't care to see if it was a binomial which became a normal distribution, or is it log normal distribution. We don't care about it. Typically consider it take a normal, let's convert it. But if you have less number of data points, then these things you have to look into very carefully. Clear? So next is Poisson distribution. We studied Bernoulli, we studied binomial, next is Poisson. Binomial is the summation of multiple Bernoullis, and this is Poisson distribution. So what is Poisson? How is it different from binomial? Both of them are discrete distributions. It expresses the probability of a given number of events. You can consider it as k, you can consider it as x, up to you, occurring in a fixed interval or space. Now this is what makes it different from binomial. Right? It occurs in a fixed interval or space. These events occur with a known constant rate. This is typically called as my lambda, or the average of the distribution. By the way, if you go to my binomial distribution, here the average value is NP, number of trials into probability, and the standard deviation is root over NPQ. I'll mention in the slide, guys, but this is what it is. Okay, in Bernoulli, we don't have the n was 1. Number of trial is 1 in Bernoulli. That is why it was Pn root over PQ for standard deviation. Here we have P and NPN root over NPQ. If I want to find a variance, it will be square of this. It will be NPQ. It will become NPQ. Okay. Okay. Now in Poisson distribution, as I mentioned, it occurs in a fixed interval in time. It also occurs with a known constant rate, and that is my average value, or what you call as lambda. Okay, its distribution can be expressed by a normal distribution if the number of trials is many times higher than number of successes. So this is again called as normal approximation, guys. Okay, all right. What is the PMF? The PMF looks like this. Okay, K means X here, same thing. And lambda is not the average number of events per interval. We'll take up some examples, guys, and then we'll study, and it becomes very easy for us to understand. I'm first going through all the distributions together, because that is when you will be better able to find out the differences, compare them and find the difference between them. And then we'll take up the examples of all these distributions together. Okay. So what is the mean value here? The mean is average is lambda. E of x means mean is lambda, and variance is also lambda. So standard deviation will be root over lambda. Okay, in this case. Now let us take an example of a binomial distribution problem statement. So a bank issues credit cards to customers under the scheme of MasterCard. Based on the past data, the bank has found out that 60% of all accounts pay on time following the bill. If a sample of 7 accounts is selected at random from the current database, construct the binomial probability distributions of accounts paying on time. So first we have to think about the expression which we had. What do we need? We need the number of trials, the probability of successes, right? So if you look at here, this was the formula which we had. Here my n is equal to 7 because my number of accounts is 7. My p value is 0.6 because 60% of accounts paying on time is what being given to, and that is what being asked. Please understand, whenever the question asks constructs the binomial probability distribution of accounts paying on time, that becomes a success. That becomes your x. So the probability of this event you have to capture, which is p, and this is 0.6. If they would have asked distribution of accounts not paying on time, then your probability would not be 0.6. A p value will not be 0.6. That will be p is equal to 0.4. But since they are asking accounts paying on time, this is the probability given, my p value will be 0.6. And hence my q will be 0.4, 1 minus p. Clear? So once we have that, next what we have, we put these values in the expression, and this is what I get. So from this, I can calculate the different probabilities with respect to different possible outcomes. What is X here? I have 7 total accounts, right? Out of them, either none of them will be pay on time, one of them will pay on time. We'll keep on going till we have a situation where 7 accounts may also pay on time. We do not know. So these are the possible outcomes which I have out of 7 accounts. Can I have 8 accounts paying on time out of 7 accounts? No, so that's not possible. Anyways, it's N7CX, right? So X will start from 0. It may start from 0 to 7. Cannot 7C8 is not possible at all, right? So X represents the total possible outcomes which we have, number of the possible outcomes which we have. So out of 7 accounts, either none of them will pay, or 1 will pay, or 2 will pay, or 3 will pay, or 4 will pay, 7 might pay. And then I have to capture the corresponding probabilities associated with each of these outcomes. And that can be easily achieved by using this formula. Let's do that. So this is my table. I have put all the values of X separately in this formula, and this is the probability which I get. I have rounded it off to 2 decimal places. So probably now the accounts paying on time is almost showing as 0, right? But maybe 0.000 something. Okay, now I can easily construct the probability distribution table or probability distribution graph. This is what it looks like. Discrete distribution again, and they should be accounts paying on time. This X represents accounts paying on time. Now let us take an example of a Poisson distribution. Okay, so customers arrive at a rate of 72 per hour to my shop. What is the probability of K customers arriving in 4 minutes? So in Poisson, we have a definite interval, right? What is the probability of K customers arriving in 4 minutes? K customers mean here, K stands for 5 for the first question. Customer, 3, more than 3, not more than 3, whatever it is. So ultimately, if we plot the distribution table or distribution graph, we'll get every possible answer, right? Here the K and the X has been defined for us, K or X, whatever you call it. And the rate is given 72 per hour to my shop. Now, please be very careful when it comes to Poisson distributions. Why? Because always look out for what is being asked, in what interval it is being asked. They're asking what is the probability of K customers arriving in 4 minutes, and what is given to you? 72 per hour to my shop, per hour, and this is per minutes, not even per minute. This is in 4 minutes. So to convert this rate which is given to a 4-minute interval. So lambda is given as 72 per hour. So this basically means I can convert to a minute. So 1 hour stands for 60 seconds. So minutes. 1 hour means 60 minutes. So this will be 72 per minute. Correct? And this value will become very simple. So this will become 1.2 customers per minute. But the question is asked in the interval of 4 minutes, not 1 minute. So we can have to convert it back to 4 minutes. So this will be also multiply numerator and denominator by 4. So actually it is 4.8 customers in 4 minutes. This is your lambda, not this. If it would be given in 4 hours, then my lambda would have been 72 divided by 4 hours. So that is how, you know, if it would have been given 4 hours, then it would be 72 into 4 divided by 4 hours. Because this is per hour, we have to convert to 4-hour interval. Whatever is being asked here, you have to convert it to that unit. Clear? So let's see. Convert it to 4.8 customers per 4 minutes. I know 4.8 customers, 0.8 customers doesn't mean anything. It should be in integers, but let us keep it for the sake of mathematical calculations. Now, what was the formula? The formula is very simple. P of K is equal to e to the power minus lambda to the power of X or K. Let me call this K since I've taken K by K factorial. This was my formula. I put the formula here for your reference. So the first question is asked 5 customers K here, right? So K will be 5. Rest everything is already given. Lambda is already calculated. And this is how I can get 17.5% as the probability. So probability of 5 customers coming to my shop in 4 minutes is 17.5. Average 4 minutes में कितने आते हैं? 4.2. 5 customers, little bit, the probability reduce. More than 3 customers, will be x is equal to k is equal to 0 के लिए होगा, k is equal to 1, k is equal to 2, and k is equal to 3, because not more than 3 means less than equal to 3. And we'll add all these probabilities because this is discrete probability. We can simply directly add it. Correct? Mutually exclusive है ये. Right? Either 0 customers will come or 1 or 2. It cannot be that 0 and 1 will both occur together. No, mutually exclusive है, so we can just simply directly add them up till 3. Okay. Similarly, for more than 3 customers, more than 3, so it will be 4 plus 5 plus 6 plus whatever customers we have. So here we see there is no limit to it. Earlier in binomial distribution, when we take the example, we took the example of accounts. We had 7 trials, right? Number of trials was 7, correct? But here there is no number of trials as such. We keep on going. We'll see how to and when to, stop, where to stop. So the last question is, what is the probability of k customers arriving in 4 minutes? And that k value should be more than 3. So what's the probability of more than 3 customers arriving in 4 minutes? So for that, I'll have to do 4 plus 5 plus, it can keep on going, right? More than 3 customers. But if you remember, as I told you earlier as well, whenever we talk about probability, total probability has to be 1 of all the outcomes, right? So if I already have calculated probability of k less than is equal to 3. So this is already I have calculated here. And the next question I am being asked, probability of k greater than t. That is what I have been asked. So this is equal to nothing but 1 minus p of k less than equal to 3, isn't it? Suppose I have these all, segments, right? 0, say 3 and 3, 2 onward. I have calculated the probability for this part. Right now, on this part, what I can do, total probability is 1 minus this part will give me this part. Very simple. So instead of doing p of k is equal to 4, then 5, then 6 and 7. So unlike binomial distributions, here we do not have number of trials. So you can keep on going, right? Till how much will you calculate? So better is to just subtract it from the other half, right? So that is how you get it. Okay. So if I want to express these two as cumulative probabilities, right? So this is how it will look like. The lower tail, this is upper tail. Less than equal to 3, greater than 3. 29.4%, this is 70.6% or 0.706 probability. Now let us try to construct the probability distribution table for this problem statement. So I'll be using what formula? I'll be using this formula, right? P of k is equal to lambda is 4 already given to me, and this value which you see here is also lambda, and this will take the value of 2.7 to something, right? E ka value, it is constant. Once I get this from here, what I'll calculate, I'll again draw the same construction table, right? The probability table. I'll have k and p of k on the table, and then I'll basically plot the graph. That is what I'll do. Same thing which I had done, the process which I had followed for binomial distribution. Right? And then finally, my distributions. So you can see here that after customers 10 or 11, the probability diminishes, right? Correct. And that is what we have done that is what I was talking to you about, right? How many will you calculate? More than 3, how many will you calculate? We don't know unless until we calculate. So we directly subtracted it from the other probability. It is always easier to do that. But once you construct the distribution table and the graph, you'll easily able to see beyond customers 12, at least, there is no point in finding out the probabilities of more than 12 customers coming within 4 minutes. It's not hard. It's not possible because the average is 4.8 customers, right? So more than that too, it cannot happen. So average is 4.8, which will lie somewhere, in this region. This is your average 4.8. So here the lambda is equal to 4.8, which lies among this point. And that is why the number of customers, 4 customers that have been 4 minutes has the highest probability. and followed by that is 5 customers, per 4 minutes. That's why 4.8 lies between 4 customers and 5 customers, the lambda value. Clear? Okay. All right. So now let us take another example of Poisson distribution. Okay. So let's say I work as a data analyst in AWM Private Limited. After analyzing data, I make reports where I had the efficiency of entering 77 words per minute with 6 errors per hour. What is the probability that I'll commit 2 errors in a 455 financial report? So what is the interval being asked here? Errors and word. 455 word is your interval, right? And what is given to us? 77 words per minute. 77 words per minute and 6 errors per hour. That is one given to us, right? So what we'll do here is we will simply try to calculate the lambda value first. That is the first thing which you have to do. But for that, we have to first think about it, right? Because words per minute is given to me and errors per hour is given to me. Somehow I have to convert these two units to errors per words. So errors and words. So let's first see how we'll do that. First, we'll convert 77 words per minute to words per hour because this is also in hour, right? So I'll have to bring them to the same platform. Either I convert this hour to a minute or this minute to an hour. Right? So I'm converting this minute to an hour. So they have to be, so 1 minute is equal to 1/60th of hour. So 60 minutes multiplied with 77, which is 4620 words in 1 hour. Next, I'll convert 6 errors per hour, which is given here, to 6 errors per 4620 words. Because 1 hour means how much? We have in 1 hour, we have 4,620 words, right? Then I can easily calculate errors per word. So this is how we can convert it. Very simple, right? Okay. So my lambda value will be 0.00129, which we have here, into 455 because I need enough 455 word interval. So these many errors per report or these many errors per 455 words. Correct? Once I have that, I can easily calculate my probability for k is equal to 2 errors in a 455 financial report. Yes. Okay. So errors in 455 word, that is your interval. Okay. Errors in 455 word. So this is actually your interval. Once I have this value, I can easily calculate the distribution table as well. It's my distribution table. I plot the entire distribution table for lambda is equal to 0.587. So for this, there's 9.6%, right? Which is 0.096. So this value which you see here is actually 0.096, the height. Okay, and you can see here, right? Only 0.587 errors in 455 words. And that's why 0 errors, the probability of 0 errors being committed in 455 words has the highest probability because this 0 is very close to 0.587, then 1. So as soon as you increase the number of errors to 1, my probability starts decreasing. Then 2, then 3. Why? Because obviously average rate agar 0.587 errors per 45 words hai, then of course 1 error, 2 error, 3 error, 4, 5 error, whatever errors are there will have less probabilities. Right? And one point of time the probability will diminish. Clear? Okay. Now, if I ask a question, so what happens when the number of words increase? If the interval changes, how is lambda getting affected? How does it influence the probability mass function? So here what I'll do is I'll calculate lambda with respect to 255, 455 and 1000 word intervals. Okay. So let's say lambda 1, I've already calculated 0.327 errors per 255 words. Lambda 2 is 587 errors per 45 words. Lambda 3 is 1.287 errors per 1000 words. So let's say these are my 3 lambda values. Lambda 2 I've already calculated, but I'm setting as a lambda 2. So I use the probability mass function to calculate the table of the x values with its corresponding p-values or the probability values, right? Okay, and I plot all the bar diagrams and superimpose it to form a grouped bar plot, which would look like this. So you can see here, as the interval here, if you look at this, as my interval is changing, my errors is also will definitely change. Agar 255 volts mein 0.2328 hai, 455 mein 0.587 hoga. But this is not linear increase. Please understand, this is happening according to the Poisson formula. Okay, for 1000 this will be 1.287. Okay, and using these different values of lambda, I'll generate 3 different tables of X and the corresponding probabilities, and I'll plot them as a group bar plot. So this green belongs to lambda 1, this red belongs to lambda 2 for P2, and this blue belongs to lambda 3 or the third table, right? Okay, so if you look at here, you can see a change in the pattern, right? From this error, green, red, blue, that was the pattern which was going on, right? Green has a lesser probability than red, red has lesser probability than blue. But when it comes to 0 errors, it had a reverse in the trend, right? It's a trend reversal. Okay. So what this basically means is that when you have 455 word as interval, right, my 0 value is closest to 0.5. So what it means is basically when the interval is 255 words, my lambda value average is very close to 0, which is 0.328. That is why 0 errors in 255 words has the highest probability. Okay. Now, as soon as the number of errors becomes 1, right, the probability of the third table, in the third table for lambda with respect to lambda is equal to 3, which is 1.27 is the average errors per 1000 words. So for 1, the probability for the third lambda will be the highest, and will keep on going in the same trend. For 0, it will have a trend reversal. That is what it basically means. So if when you change the interval, it's always interesting to see how it affects my probability mass function. So I have here 3 probability mass functions superimposed for 3 different rates of lambda. Okay, we'll do all of these exercises, guys, in Python also. Okay, we don't have to remember all these formulas. Okay, we'll have one specific function and we'll use that to calculate our probabilities in Python. So check out our Python application video for this particular session. And the next upcoming videos will be dealing with continuous probability, dealing with probability distribution for continuous random variables. So till now, what we have studied, we have covered, I guess, binomial, Bernoulli, and then we had covered Poisson. In Bernoulli, we had P as the P and Q as the parameters, binomial NPQ as the parameters because number of trials is greater than 1, right? A number of Bernoulli processes gives you a binomial. Poisson, we had lambda as the parameter. Okay, so we saw how these probability distribution function looks like. It has its own formula with respect to different problem statements. We also understood them with the help of examples. We'll be doing all these things in Python as well. Okay, so next video we'll be dealing with continuous distribution. So wahan pe we'll have normal distribution, Gaussian, log normal, all these with their own set of parameters, just like we have it here. They also will be trying to understand with the help of examples, and we'll do those in Python as well. Okay, so stay tuned, guys. See you in the next video. Thank you.